Alright, and I will give you some introductory remarks, theoretical development, and some comments on the method, and we'll try to illustrate our experimental results and concluding remarks. Again, this method now has been using quite often in NASA now. So it's simple, but you can understand about the physics, the physics behind the mathematics equations. Okay. Now let us look at those approaches to control. There are many hundreds or thousands of textbooks in control. There are a lot of control approach. Most of the textbooks still in the conventional control approach. Means you have to have a system model. And how do you know your system model is correct? You gotta go to the experiment. And then you design controller, just what you have learned so far. Like my homework number 9, I give you model. Okay, this is model design control. Then how do I know the model is correct? Tell me, how do I know the model is controlled? How do I know the model is good? How do I know it? When Newton law is always good, and Newton law is nothing wrong. And when you apply it, it's more complicated than just Newton law. Okay, so the equation I give to you, based on Newton law, that's the ideal case. Now, how can I verify my model is good? How can I do it? What should I do? Huh? Any suggestions? How can I verify my model? Comparing with what system? The real system? Then yeah, but what is the real system? How can you compare? How do you compare? Experiment? Yes. So, you gotta go to do some experiments to verify your model is good. Now, all the model so far today, almost all the model, including aircraft model, they use linear model. The linear model. We call linear model. Alright? But most of the system model is nonlinear. Alright? It's a simple example. What is this model? This is M. Say this is mass. And I have gravity here. This is Z. And I have theta here. So, what is the model for this? Do you know? Anybody know? What is the model for this? Simple model. Now we know that it's pendulum. Right? It's the pendulum. What is the pendulum model? We have a theta double dot plus square root of G over L theta. Is that model? Assume I don't want to talk. Sorry, this is G over L. Think so? This is our model. Huh? Pendulum the model. The crack. The classical crack. Is that true? That means, well, if you want a Newton law ML theta double dot plus MG theta equal to 0. Is that true? This is true now. No? To be accurate, this is must be like that. Right? Agree? Right? So this is, but when theta is small, the knots come like that, right? Just this simple problem. Just look at this simple problem. This simple problem gives you this. And this is nonlinear model. Okay? This is nonlinear model. But so far, we learned from February till today, we all use linear model like this. That's my linear model. Agree? Because that gives me theta double dot, for that give me this model. And G is constant, L is constant, so theta double dot plus G over L theta equal to 0, and my frequencies is equal to omega is the square root T over L, right? So in matter of fact, our clock moving this way, not this way. That means what? That means all the control method we learned today so far is useless. Right? Yes? Because we assume they are all linear model like this. But actually it's like that. Agree? It's a simple model. It's this. That's not quite right. Even if this nonlinear model, we design a controller with this linear model, it's useful. It's useful. Because of what? For example, I just simply give you a simple example. If I say I have a feedback here, I say I have a simple feedback. ML theta double dot plus MG sin theta, and that's my torque. Assume my torque is a constant zeta times theta dot minus. Matter of fact, this system, if I have a feedback, just simply theta dot there, this system still stays. All right, so it doesn't matter if it's nonlinear system or linear system. What you can do is you can still use the linear system model, design a controller, and go out there and go back to try it, see if it works or not. Agree? All right. That's why we have the second bullet here we call adaptive control approach. Why we need adaptive? Simply because, one, our system may not be linear. There could be nonlinear. All right. Our system may have a lot of uncertainties. For this system, what kind of uncertainty we have? This simple pendulum, what kind of uncertainty we have? Anybody give to me answers? this, in ideal case, that's in space. If on the ground, this system subject to what? To air. So there's aerodynamics involved. Agree? And then what else? We assume this is massless. No mass. But that's true. That's true. That's true. That's not true. That's not true at all, right? There's some mass there. So these ideal equations does not really represent this system at all. So you have uncertainties. We call uncertainties. But again, we can consider those are just uncertainties.